Right, this is a practice set of questions for Edexcel IGCSE. These are taken from Save My Exams website. Let's just get cracking. This first question, y equals 1.8 correct to one decimal place. Calculate the lower bound for the value of 4y plus 1. Well, if the lower bound of 1.8 to one decimal place, or if 1.8 is to one decimal place, then the lower bound would be 1.75. So that is the lowest number that it could be to give a value of 1.8 when expressed as accurate to one decimal place. And the upper bound is 1.85. That theoretically is 1.849999, well, 49 recurring, but for the purpose of these, you know, we take them as the same thing. So that is the upper bound, therefore, of y. So the upper bound of 4y plus 1, well, what we want, we have to go through these and decide, do we want the upper bound or the lower bound? In this case, it's a very simple, straightforward example. Obviously, the upper bound of this expression occurs when we have the upper bound of y. So that's going to be 4 times 1.85 plus 1, which is 8.4. So 8.4 is our answer for that question. That's how it works with upper bounds. Let's go on. Right, okay, we've got a circle theorem. This is a fairly straightforward one, this, I think. They get quite a bit more complicated than this, but this isn't too bad. A, B, C, and D are points on circle center O. Cyclic quadrilateral, of course. ADB equals 57. That's this angle here. And BCD equals 106. Calculate the size of AOB. AOB, well, here we're just applying a single circle theorem rule, and that is that the angle of a chord at the center is twice that at the circumference. So if that's 57, then this angle here is going to be 114. And then the next part, it says, just at the bottom of this, it says calculate the size of angle BAD. BAD being this, well, of course, this being a cyclic quadrilateral, opposite angles add 280, so this one is going to be 74 degrees here. Okay, so that is relatively straightforward. This one is on proportionality. P is indirectly proportional to the cube of Q. When Q equals 15, P equals 1350. So this proportionality statement we can write like this, and it gives rise, we can convert it into an equation if we apply this constant of proportionality. Now this is all, this is fine, except that the equation isn't very useful unless we can actually find that constant of proportionality. So we need a boundary condition in order to allow us to do that. We're given that boundary condition, that's Q equals 15, P equals 1350. So if we substitute those into this equation, then we're just left with the unknown sitting on its own. We can resolve for the unknown, or we can solve for the unknown, and that gives us 2.5, K equals 2.5. I tend to use K as a constant of proportionality, and therefore P equals 2.5 Q cubed. It goes on to say calculate the value of P when Q equals 20. Well, we just substitute 20 in for Q, and that's going to give us P equals 20,000. And that is that. So it's a really straightforward one. Okay. X equals A times 10 to the power of n, where n is an integer, and between, displaced there, root 10 and 10. Okay. So x squared, if we just square both sides, is going to be a squared times 10 to the power of 2n. Now it says express it in standard form. So because this is between 10 and 100, we're going to have to scale it down. I mean, it's between 10 and 100 because A is between root 10 and 10. So this number A is going to be something like, 30 or something like that. So 30. So if it's 30, then A squared is going to be 300. So we're going to need to divide A by 10. So if we're doing that, we're going to need to add. We're going to need to put a factor of 10 into this second part. But of course, we're doing it by A squared, so that's going to be a factor of 100. So it's going to be that. So we can say that's the same as A squared anyway, can't we? Times 2 to the power 10 to the power of 2n. Okay, so this number A over 10 is between 1 and 10. So we could write this, couldn't we? So that makes it sort of valid. And anyway, we need to group the 10 squared and the 10 to the power of 2n together. And that's pretty straightforward. So we're going to represent that as 2n plus 2. So that is it, really. All right. It's a slightly odd question, this, because we've not really ended up with A here, have we? But anyway, so that's what it is. Okay, next one. Question 5. ABCD is a rectangle, not accurately drawn. Well, we can see it's not actually a rectangle, isn't it? It's more like a parallelogram. But anyway, and it gives us the sizes of the sides. AB is 10, BC is 8, and then we got these points P, Q, R, S on the sides of the triangle. So that's X, that's X, that's X, and that is X. So we're asked to show that the area of the quadrilateral PQRS is given by this formula. Well, the area of this PQRS is going to be the total area of the big rectangle minus these 4 squares. Well, because what we can imagine, we can glue this triangle together with this one, and that makes a sort of a rectangle, and this one with this one, just makes the calculations a little bit easier. And so what that's going to give us a total area of 80, that's the big rectangle, minus this rectangle that we put together as a result of that, and that, which is x wide and 8 minus x in the other direction. And this second one, second rectangle made by those two, which is going to be x times 10 minus x. Right, okay, so we just expand that, group like terms, and we do indeed get 2x squared minus 18x plus 80. Okay, good example of us forming an equation. So we've done that, found the area. Okay, and then we've got sort of second part here, part B. So if that is the equation for the area, find dA dx. So there's a bit of differentiation. So dA dx is the rate of change of the area with respect to the value x. So just using the power rule, because this is just a straight polynomial, we get 4x minus 18. So that's 2 times 2, take away 1 from the index, that's 4x. And then this is x to the power of 1. So 1 times minus 18 is 18, and take 1 off the index, that's x to the power of 0, which is 1. And then this, of course, this 80 is 80 times x to the power of 0, effectively. X to the power of 0 is 1. So if we multiply the 0 in the index by the 80, well, it just, a term disappears. So that is the derivative, 4x minus 18. at the minimum point, if we were to draw a graph of this function, you'd see it's a quadratic. It goes down and then back up again. We want to find the value of x that gives us that minimum. So at the minimum, of course, what happens is the gradient is 0. That's the tangent at the point at the bottom of the curve. The gradient, that's the gradient. The rise over the run is 0. So the gradient is 0. So this dx is equal to 0. So true of turning points is that the gradient, which is the derivative, is equal to 0 at that point. So we can actually equate this to our derivative function here, and that's going to give us x equals 4.5. How do we know it's a minimum? Well, we know it's a minimum because this function is a positive quadratic, so therefore we know it has this shape, this bowl kind of shape. Right, solve the simultaneous equations. There we've got two simultaneous equations. I mean, this we can't apply our sort of linear trick where we scale and then add or subtract the equations here. We basically got to find a different way of eliminating one of the unknowns. In this case, it's fairly straightforward to eliminate y. So if we rewrite the second equation, but with our expression for y in there instead of the y, we get this. And then if we expand that out, we're going to get that, which rearranged gives us this 5x squared minus 12x plus 7 equals 0. Now, if we're going to factorize this, we can explode the middle. So 5 times 7, that's this, the 5 times the 7 is equal to 35. So if we're looking for two numbers that add to minus 12 and multiply to 35, then we can easily come across minus 5 and minus 7. So if we split the middle into minus 5 and minus 7 x, we've got 5x squared minus 5x minus 7x plus 7. And then if we factorize each of them in pairs, it gives us 5x into x minus 1 minus 7 into x minus 1. And we can group the 5x with the 7 like this, and it gives us a solution of x equals 1 or 7/5. So that is that. And just to recap, what we need to do with the simultaneous equations is eliminate y. And if it's not a sort of two linear simultaneous equations, then it doesn't matter, because this is really what we need to do is to actually kind of trade in our y for some x's. Yeah. Okay. The diagram here shows a solid cylinder and a solid sphere. They both have radius r, and we're told that the total surface area of the cylinder, that means that you've got to include the top and the bottom, divided by the surface of the sphere, is equal to 2. And then it goes on to say find the ratio of the volumes. So the total surface area of the cylinder, we just write this out. We don't know what the height is. So we have to put, if we don't know something, but you know, we'll create a variable. I could say let the height equals h here. I've omitted that, but that is what we've got. So this is 2 pi r squared is the top and the bottom. The top and the bottom, each pi r squared, and then the curved surface area is 2 pi r, which is the circumference times the height. And then the total surface area of the sphere is 4 pi r squared. That's a standard formula. So so this over this, it's telling us here in this equation is equal to 2. So if we just put the ratio of those together, Well, we're just going to work that through, basically. We can solve that for h. You can pause the video and just look at the steps if you like, but that's going to give us h equals 3r. So now we can go to this second ratio here. The volume of the cylinder is going to be equal to pi r squared h. So that's the area of the base times the height. And because we know that h is 3r, then we can substitute that. We get 3 pi r cubed. Total volume of the sphere is 4/3 pi r cubed. Again, standard formula. So if we divide one by the other, cylinder by the sphere, we're going to get this. The pi r cubes go out. That is a cube there at the bottom. It doesn't look like it. It is. And we get 3 divided by 4/3. We divide by a fraction. We multiply by the reciprocal of the fraction. That's 3 times 3/4, 9/4. Okay, so that is what that is. All right, let's go on. Now this is an interesting one here. Right, we see a lot of these. An incomplete histogram and table give information about the ages of people living in a village. Okay, so we're just given these sort of grey blocks here and this table here. Now the thing with and these frequency bands here are not all the same width, and this is why we've got frequency density, because in a frequency density chart, the area of each block basically, well, represents, or we could say is proportional to the number. Okay, so see how we write that. So the area is proportional to the frequency, the number. So just going back to what I was saying before, is we can turn our proportionality statement into an equation if we put this constant of proportionality in. So A equals KF, and turning that around, the frequency equals A/K. All right. So now the key thing here is we've got to find this K. And once we do that, we can everything else kind of follows on from it. So let's have a look. In the case of so in order to do that, we need to know, we want to know the area, we need to know the width and the height of these. All right, we don't know the height of this bar when we set out, or for 0 to 10, and we don't know the height of 50 to 75, nor 75 to 80. In the case of 15 to 30, we don't know the frequency, nor 30 to 50. So there's only one sort of complete set of information that we can use, and that is this band. And this is frequently the case with these questions, but that's all we need. So when we look at 10 to 15, it's got a width of 15, hasn't it? We can see that it's got a height of 30 in this chart. So therefore it's got an area of 150. Okay, so if it's got an area of 150 and a frequency of 60, that tells us that our constant, or that's like an exchange rate, isn't it? A proportionality constant is 2.5. Now the 2.5 is going to apply to all of them. They're going to all have the same scaling factor. So now we know that, we can actually complete quite a bit more. So in this first case, if that is 2.5, then we can find that the area is going to be, well, it's going to be the constant times the frequency, as per here. Constant times the frequency. So 2.5 times 100, that gives us 250. And then since we know that the width is 10, we know that the height therefore is 25. Width times height equals area. Okay, so and then we can basically go through and do the same thing for down here and down here. Now we've got the width and we've got the width, height, and area for these two bands. What we don't have is the number, but now we can actually work this out. The frequency is going to be equal to the area divided by the constant. That's the area. That's the constant. That's going to give us 120, and then 100 here. So we basically completed the whole thing. And then we can draw the bars on here because we know the heights for each of these widths or class widths, and we can complete the frequency for those that we don't know. So yeah, so that's how it's done. So I think the key to this really is you know, we'll always get something that looks like this with a you know, a class width and then a frequency. And so if we just add a few more columns ourselves, the width, the height, the area, and then the constant, which is the area over the frequency, then we've got the framework for doing it. We'll find one of these rows allows us to work out the conversion constant, the constant of proportionality, K. And once we've done that, we can reapply that to find the areas and the heights and the frequencies. All right, so that's basically what. Okay, so that is that. Alan has to attend a meeting on Monday and on the Tuesday. Probability is late for meeting is 1/8. Not very good. I don't think I want him on my team. Complete the probability tree diagram. Late, not late. Okay, so we're drawing it over here. Late. So if it's the probability of an 8th being late, then the probability of not being late is 7/8. So, you know, for each from each node. So this is a node, that's a node, that's a node. From each node, the probabilities will add up to 1/8, 7/8 is 1. Okay, so so if he's late on a Monday, then there's two possibilities. On the Tuesday, that he's late or he's not late. Again, the probabilities are 1/8 and 7/8. So again, they are 2 to 1, and we've got the same thing here. Now, if we multiply these out, what we get, I've just used a bit of notation here, LL, is the event that is late on both days. So we can multiply across. These are independent events, so we multiply them across. We get 1/8 times 1/8, a 64th, in other words. And then late on a Monday and not late on a Tuesday, ln is 1/8. This 1/8 times a 7/8. There we go. That's 7/64ths. Similar thing for this third row, 7/64ths. And then the probability is not late at either meeting. Is thankfully it's the greater probability of them all. Not NN. We've got 7/8 times 7/8. That's 49/64ths. Now, so we multiply across with the probability trees, we add down. These are mutually exclusive events. We're either got, you know, one of these, but we can't have both. You know, we've got to have just one of them. All right, so we can add those down, and that will add up to 64/64ths or 1. And then it goes on to ask us, calculate the probability that Alan is late for at least one of these meetings. Well, that basically is going to be the first two rows. So what we're doing is we're adding these three. These are the mutually exclusive events that satisfy our condition. So in each of these cases, he's late for at least one meeting. So we could just add these up. That'll be easy enough. So the but late for at least one meeting. So so it's the sum. We give them the probability that he's late for neither there, but the probability that he's late for at least one is going to be 1 + 7 + 7/64. That's 50/64ths. So that is what we should have. Okay, so write it there. Okay, so so that's what that is. Probability tree. Show that the recurring decimal point 396 recurring is equal to 44 111ths. Well, the thing to remember here is that anything that's recurring, and this notation here with the dots there means that this decimal is 0.396396396396396. We need to take the recurring part, and if it's got 3 digits, we put it over 999. If it was just 2 digits, it would be over 99. If it was 4 digits, it would be something, you know, so many. If it's just 1 digit, like 0.3 recurring, then that would be over a single 9, so that would be 3 9ths. So just to kind of illustrate that a bit more, 0.3 recurring equals 3 9ths equals 1/3. We already knew that, didn't we? So so in this case, we've got 396 divided by 999, which if we divide through the numerator and denominator by 9, we get 44 111ths. This is a nice simple example because the whole of the decimal part is recurring. And so if that is not the case, and there'll be further examples that can show this, then what we need to do is we would need to scale this accordingly. So just by way of an example, if what we had was 0.0396 recurring, then we would have to express that as 1/10 of 0.396, which would be 1/10 of, well, 396 over 999. We should put those in there, and then obviously that's going to work out to be 44 over 1110. Okay. So, you know, in other situations, we may well have to do this sort of scaling idea before we can get to our answer. Okay, so what else have we got? Functions, function notation. F of x is 2 over x, g of x is x plus 1 over x. State which value of x cannot be included in the domain of f or g. Well, we can't have 0 because it would be divided by 0. So x has to be excluded from the domain. Everything else is in. So solve g of f of a equals 3. Well, first of all, we've got to work out what g of f of x is in order to do that. So we've got what we're doing is we're substituting f of x into g of x. For every value of x in here, we're going to put the f of x. So that's why we've got that. So that x becomes 2 over x, and this x becomes 2 over x. And then if we work this through, that's going to be 2 plus x over x divided by 2 over x. And if we divide by a fraction, we multiply by its reciprocal. So that's what we've got there, x over 2, and that comes to 2 plus x over 2. So if we're to evaluate g of f of a, I don't know what a is yet, but it would just be this. We're just substituting a in for x, 2 plus a over 2. Now our equation says that that is equal to 3. So then we can just solve this equation for a, and that's going to give us a equals 4. Now it says express the inverse function g minus 1 in the form in this form g minus 1 of x. So if g, we're just written g here because it's simpler to manipulate the letters. G is equal to this. Now, in order to do this, we have to change the subject of the equation. We have to make x the subject. So to do that, we're going to cross multiply. We're going to group all our x terms together. Gx minus x, bring this over, is equal to 1. Therefore, x is 1 over g minus 1. Now, that's kind of what it is, but we always express it as, a function in terms of x being the sort of the variable of the function, if you like. So we need to swap these over, or we need to put x in there. So the inverse function is going to be equal to 1 over x minus 1. Okay, so hopefully that's been useful. That's popped us off the bottom of that set of questions. So if you can understand those, then hopefully you'll be in a good position to tackle similar questions in any IGCSE examination. Okay, so that's it. Thanks for listening.